Hello and welcome to the module Robot Dynamics. So before we start, let us quickly look at the overview of what we are going to cover today and in this module. So today we'll be discussing robot dynamics. Why is it important? How is it done? Various aspects of robot dynamics. How is it beneficial in robot design, controller design and all. So I'll also introduce you to forward and inverse dynamics, why they are used and why they are important, how they are done. So different approaches to robot dynamics, that is Lagrange-Euler approach. So we'll start with this today, and potential energy, kinetic energy, effects of gravity. Finally, we'll reach to dynamic equation of motion of an arm. We'll also discuss Newton-Euler approach in next few classes. Okay, and there are many other approaches to dynamic equation of motion. So that is recursive formulation and Denock based approaches that will not be covering in this module. However, please note this module is for academic students who are both basically in UG, PG and PhD and research students. However, for industry students who are from industry, they can quickly go through this module without going too much deeper into it if they are not interested in research aspects of it. But yes, that will help you to understand still the functioning of a robot controller and why is your robot performing this way. If at all it is performing badly, why is it so bad? If it is so good, why is it so good? So you will be in a position to understand the behavior of your robot. So still that will be useful. Sometimes in advanced application and complex methods where we follow to implement our robot algorithms, this may still be very useful to the industry students also. So yes, let us just quickly start. So yes, why do we need robot dynamics first of all? So it allows us to do analysis of motion in particular links of the robot due to its own weight, how does it behave, external forces, how does that affect the robot motion, okay, external forces or moments if it is there from outside, okay, and we can closely understand the behavior of a robot if it is commanded to give a particular kind of trajectory to follow. How much would that be possible? First of all, if your robot has got sufficient moment of inertia and masses at particular locations, so whole of the link is fully defined. Now with that set of moment of inertia and masses and the architecture of your robot, whole of the equation of motion will try to derive. So that is what is done in robot dynamics also, that we will begin today also. Okay, so to study the torque and forces that causes motion in a robot, or if a robot is in motion, what torque and forces are going to come at the joint level. So that is what is easily understood by dynamics. Okay, so to develop dynamic equation of motion that describes the dynamic behavior of a manipulator. Why is it that extracted? That is to develop a controller for a robot that works in a real hardware or sometimes for simulation purpose also, even to sometimes to design animation or maybe just a cartoon also. Nowadays with advanced features of your cartoon character design softwares, they also use this dynamic equation of motion for various lumped body or sometimes solid bodies if they are using it. Okay, so that is useful for various other reasons also, not just in robotics over here. Okay, so to design the links, to design bearings, to transmission systems and actuator selection, that is very important, because it is the actuator that is going to handle everything, ranging for your torque, so for the forces, for external forces, for the payload, for supplementary load. So everything is going to come on the actuator. So this will help you to understand this equation of motion, what we are going to derive through dynamic algorithms. Okay, so that will be useful to understand that kind of behavior of your robot and to select a particular kind of actuator for a given robot design. Okay, so yes, what is forward dynamics and what are inverse dynamics. So first, starting with forward dynamics. So forward dynamics are required to find out the response of a robot arm corresponding to applied torque or forces at its joints. So if at all you have a robot, okay, you have certain torque over all the joints, okay, all the joints. So how is the end effector going to behave? So is it going to move with certain velocity which is uniform all over, or it is going to have increasing velocity at the beginning, going at a constant speed, and then decelerates and finally comes to stop? So everything will be defined by the kind of joint torques and forces which are there at the robot joint. So that is what is forward dynamics. Okay, so you apply a torque and force at the joint and you study the effect of end effector motion. So that is what is forward dynamics. So under any given joint torque and forces, so we compute the resulting motion. So what all motions that we do? We study acceleration, we study velocity, and sometimes if it is point to point motion, we study also where it is going to stop. So that is the position characteristics also we can study of the robot as a function of time. This is very, very important. That is, as a function of time we are going to study. It is not that it is going to start today and stop tomorrow. Everything is with respect to time we are talking about. So we are very particular about kind of acceleration behavior or velocity behavior when even if it goes from a point to another point. Okay, so it is primarily used for computer simulation of the robot, which shows how a robot should follow a given trajectory under given forces and torques that is at the joint. So not just for simulation, so it will help also you to it will also help you to understand the behavior of your real robot if it is given by same amount of forces and torque. So simulation is nothing but offline visualization of your real robot most of the time. Okay, so what is inverse dynamics now? So it is to find out the actuator torques and forces that are required to generate a desired trajectory. Okay, so it is other way round. So in the forward kinematics, you applied the torque at the joint, you saw the end effector motion. Okay, so over here it is reverse. So you are given a particular end effector velocity and now you are supposed to find out the joint torques and forces which is responsible to give such kind of motion. Okay, so an efficient inverse dynamics model becomes extremely important for the real-time model-based control of the robot. Okay, if you are using this kind of algorithms for model-based control, we'll look upon control algorithms later in other module of this course. So in which we'll be using forward and inverse dynamics both. Okay, so where it will be much more clearer to you. Okay, it will also help you in selection of actuators, you see, and other parameters of the robot. Let us say you want to make your robot with certain moment of inertia of the link and masses of your link and external forces. So now in order to create a certain kind of trajectory which is the applied trajectory you want, okay, so what kind of actuator you should have that has the capability to give you that. Okay, so the torque behavior corresponding to the end effector motion or even the joint motion. Okay, so what is the requirement? Okay, so you will understand the requirement over there. Accordingly you will select a particular actuator for that particular robot. Okay, so that is what is inverse dynamics. There are various kinds of algorithms that help you to get through equation of motion for a particular robot. Few of them, as I have named earlier, Lagrange-Euler approach and Newton-Euler approach. So today we'll start with Lagrange-Euler approach first. So how does that help you to arrive at equation of motion for a given robot system? Okay, so yes, so Lagrange-Euler formulation requires the knowledge of kinetic and potential energy of a physical system. So this is an energy based approach. Okay, so Lagrange-Euler formulation is defined by this equation, the one which is here. Okay, what it is time derivative of partial derivative of Lagrangian with respect to the joint variable. So what is different parameters which are here? L is known as Lagrangian. What is that? It is kinetic energy minus the potential energy of the system. So that is known as the Lagrangian, which is here. K is kinetic energy, P is potential energy. So L is Lagrangian. Okay. Q is the angular or linear displacement of the joint. So Q is the joint variable. Okay, and psi I here is generalized force or torque. If it is rotary actuator, you see over here it is torque. If it is a prismatic joint, that will become your force, okay, for any particular ith joint. So this is an equation for ith joint. So you have to repeat the whole of this equation, this Lagrange-Euler formulation for each and every joint. We'll see by example also. We'll see by example. So it is not just this Lagrange-Euler formulation is not just for robot. It is for many other systems. Any other mechanical system can use this. So let us begin with the very beginning of our study, that when we did spring mass damper system in physics. So let us start with a small system with just one mass which can slide over the platform which is here, which is perfectly flat without friction. Okay, mean position is marked by this dotted line, and this mass is moved by a small displacement x along the x-axis of the coordinate system. Let us say it is having no motion along y, it is making perfect contact with the surface, sliding on that. K is the stiffness of the spring which is attaching this block over here, and it is attached to the wall over here. Okay, so this is how it is defined. Whole system is defined. So how many degrees of freedom is there for this system? It is just 1 degree of freedom. Okay, so let us start using Lagrange-Euler formulation for this. So for the given displacement x from the mean position, how much will be the kinetic energy? So kinetic energy here will be, for let us say if it is at a displacement x, so velocity over there, let us say it is x dot. X dot is nothing but derivative of x with respect to time. So kinetic energy will nothing but it will be 1 by 2 m v square. So it finally becomes 1 by 2 v is this, if I tell. Okay, so it is 1 by 2 m x dot square. So this is what is kinetic energy at any instant of time. So any instant you have velocity which is given by x dot. So how much is the potential energy? Potential energy here is only because of the spring extension, okay, or compression. If it is on this side, it becomes compression. So you know by basic physics, so 1 by 2 k is the stiffness of this spring, okay, and x is the displacement, so it is given by 1 by 2 k x square. Stiffness is defined by force developed by the spring for per unit displacement of the spring. So that is how it is defined. So potential energy is this. So Lagrangian becomes L is equal to kinetic energy minus potential energy. So this minus this. So this is your Lagrangian. Now I'll apply Lagrange-Euler formulation which is given by this. As because it is a linear displacement, so you should see force over here. So what earlier was psi I, which was generic force and torque, now it is confined to force only, and it is just 1 degree of freedom. So I is just 1 and there is no other joint over here. So I'll use Lagrangian now. So talking about the first part of this equation, that is this one. So that is dou L by dou x dot. So it is partial derivative of L with respect to x dot, that is the velocity. So taking derivative of whole of this now, so this goes here. Okay, so dou by dou x dot. So applying it to the first term of it, so that only remains. So this is equal to 1 by 2 1 x dot square. So derivative of x dot square will be 2 times of x dot. Okay, So the second part turns out to be 0. The derivative, partial derivative of second part turns out to be 0 because there is no velocity over there. It is partial derivative minded. So that gives you 0. So effectively what you get here is dou L by dou x dot is equal to mx dot. So this part is mx dot. Okay. Moving ahead, taking time derivative of that. Okay. So what it should give you? D by dt, that is time derivative of this. So it gives you derivative of mx dot, time derivative of this gives you this mx double dot. So it is mass into acceleration. Okay. So that is the first part of this Lagrange-Euler that you have obtained. Now the second part, dou L by dou x. So dou L by dou x. So again, starting with this doesn't have any displacement over here. This has it. So the second part will go as 1 by 2. Negative sign will remain 1 by 2 k, that is constant. So x square, derivative of x square should be 2 times of x. So again this 2 goes. Finally you are left with minus of kx. Okay. So finally you have both the terms in your hand, this term as well as this term. So putting them together, it gives you mx double dot plus kx should be equal to external force which is applied. So if at all there is no external force, it becomes mx double dot is equal to minus of kx. So that becomes your dynamic equation of motion. So this is what is known as equation of motion. For in this case it is a spring mass system which has no friction, there is no damping. Okay, so using Newtonian mechanics also you can derive it. So sum of all external forces, all the forces should be equal to mx double dot because there are no other body which is there. This is the only force that you will see, and that is due to the motion of this body only. Synthesizing that for free body diagram you can do, and you can get to the same expression, that is force minus spring force, external force minus spring force should give you mass into acceleration. Okay, if at all there is no external force, you will reach to the same point. Okay, so this is exactly similar to this. So you can do it with simple physics. So now the question arises, why should we use Lagrange-Euler in this case? At least in this case you have just 1 degree of freedom. You can isolate the body, you can make free body diagram. So it is quite trivial doing that. So you can very well follow Newtonian mechanics, your age-old system that you have been using through your school days. You have been doing it. Simple force balance, you can do it. But yes, in case of robotics, when the bodies are lying freely in space, multiple bodies are there which are connected. Okay, so it becomes very, very difficult to follow this kind of equation to create using Newtonian mechanics. Okay, so in that case, energy based technique like Lagrange-Euler formulation will help you. Okay, so that is the reason we are doing it all here. Okay, so now let us start with general system. We'll extend upon that and finally we'll reach to a robot. So this is how a one link pendulum or an arm is given by this. So it is attached over here. This is your mass. So make things simple, I have taken a concentrated mass at the end which looks like a pendulum here. So it is nothing but this is your reference frame about which this link substance and angle theta, it has a mass, so it will have a gravitational pull along the direction of g if it is like this. Okay, so it is mg which is like this. This angle will also be theta. So you have analyzed similar situation quite number of times earlier. So this system is very, very simple for you. So this will be your perpendicular component. So that will be given by mg sine theta. So this angle is equal to this angle. So you can project it like this. And the one which is over here, this force is mg cosine theta. So that is giving you just the tension in this link. So this is a solid link. So you will see a kind of tension because of this force only. Okay, but yes, if it is moving, definitely it will have other forces also. So it should be m r omega square. M is the mass, r instead of r you should see L over here, omega is the angular velocity. So that is the centrifugal force, that also will be added to this. So finally that will be the tension in this link. So we are not concerned about the tension in this link until unless we are here to design this link. Otherwise, in order to study the motion only, so we are concerned only with the force which is creating the motion. So this is the force which is creating the motion. It is given by mg sine theta into L, that is effectively the torque that comes over here. Okay, so that is what is creating the motion. Okay, so let us do the same whole analysis using Lagrange-Euler technique. So with this as a reference frame, which is here, this is your x direction, this is your y direction. So x should be equal to, if this is L, it is L sine theta. So displacement of this bob, if it is projected on x-axis, it is L sine theta, correct? So that is your x. So how much is your y? If it is totally at the bottom of this trajectory, so when it is here, so this was L, is it not? So this total length was L. So when it goes to this point, so it is till here. Now the projection comes here. So how much is from here to here? So till here it is L cos theta. So total was L. So you see it is L. L minus L cos theta is the displacement what it has done. So when it goes from this point to this point, so the displacement which is there is L minus L cos theta. So y displacement is given by L 1 minus cos theta. So this is how it is derived. So that is your y, this is your x. Okay. So yes, so if you take derivative of that, you will get velocity along x, velocity along y. Taking derivative of these two, it should give you this. Okay. Squaring and adding them should give you the velocity at this point. So this is your velocity, which is given by velocity along x square, velocity along y square. So that will be your v square. So v square is nothing but squaring and adding these two should give you this effectively. Cos square theta plus sin square theta is equal to 1. So effectively you get v square is equal to L square theta dot square. So you can reach here directly also. V is equal to r omega. So our radius over here is L, omega is theta dot. So this is what is your V. You can reach directly here, but I have followed this way because if at all you have multiple links connected in series, so this should be the approach you should go for, because you have other links also. One of them supports this direct approach, whereas other links you have to go through this channel. So that is the reason to begin with you should begin like this. So finally V square is equal to L square theta dot square. So you can directly write your kinetic energy like this. So it is 1 by 2 mv square. So it is m v square. So v is this. You got the kinetic energy. Now how much is the potential energy? It is mg. This was your lift from bottom most position to the next position. It is L 1 minus cos theta. It is mg is the force. This is your displacement. So it is your potential energy. So you know now kinetic energy, potential energy is here. So Lagrangian is kinetic energy minus potential energy. You got the Lagrangian. Once you got the Lagrangian, you can start doing your stuff. So this was the expression. I have just transferred it here also. Okay, and this is your Lagrange-Euler formulation. So going through the derivation of Lagrange-Euler is beyond the scope of this course. That should be of interest for students who are interested to do higher studies and do advanced studies of robot and multi-body system dynamics. So for them this should be very, very useful, but for industrial robotics students that should not be very much of a concern, but yes, we'll be using this directly now. Okay, so this again will start here. So as because this motion was about a rotary joint, So this time I'll use torque over here instead of force. Rest whole of the equation remains as it is. So instead of generic force and torque, this time it is for this joint is 1 degree of freedom system and rotary joint, so it is psi I becomes equal to torque. Okay, the same equation can give you force as well as torque depending on type of joint it is. So instead of qi, which was the joint variable over here, so it is theta I. So in earlier case it was xi. Why? Because it was linear displacement. This time it is theta I, that is rotary displacement. So if it is rotary displacement, angular displacement, so this is your torque. Got it? So formulation remains the same. So let us begin with this Lagrangian what we have just derived. So again the part which is here, I am using this as a Lagrangian, taking partial derivative with respect to theta dot. Only this term has it, this one doesn't have, everything will be treated as constant. So it is 1 by 2 ml square, theta dot is square. If you take derivative, it becomes 2 times of theta dot. So you can strike off 2 from numerator and denominator, finally you reach here. Is it not? So again taking time derivative of that will give you, time derivative of this should give you ml square theta double dot. Okay, so this is quite trivial, you know it. So again the second part, this part, if you take dou L by dou theta, for this will be treated as constant. There is no theta over here, only this part is there, and even for that this is a constant, only this part remains. So cosine derivative is sin A with negative sign, so negative negative, finally it is positive, and again due to cosine it is negative, that remains here. mg will remain, mgl will remain. So this is your second part of the Lagrangian. Okay, so now putting them together, so you get to this, the first part and the second part. So negative, again over negative here it becomes positive. So this is your equation of motion. This is your equation of motion. Got it? So it is dynamic equation of motion of a one link pendulum or an arm. If it is a arm which has just 1 degree of freedom arm, one link system, so it is driven by a torque and it can give you a motion. So in this case, if it is torque, any external torque is 0, it becomes a simple pendulum, otherwise it is a one link robot. Okay, so that is a simple pendulum now. So in that case tau becomes equal to 0, and this is your equation. You have done it plenty number of times in your high school days also, you will remember it just now. So theta double dot is equal to m goes off, L square and L goes off, so finally you are remaining with theta double dot is equal to minus g by L sin theta. For very small value of theta, sin theta tends to theta, and you can write it like this. So now you can recall it is what? It is simply omega n is equal to square root of g by L. What was omega n? It is the natural frequency of this system. So this becomes a simple pendulum which can make simple harmonic motion without any external torque. So it can keep on oscillating. If there is no friction and other losses, it will keep on oscillating like this. So this is how you can arrive to same old physics equations using Lagrange-Euler's treatment of simple pendulum also. Okay, so the same can be obtained using Newtonian method as well. If you can create a torque balance equation, draw an isolated free body diagram of the pendulum, and you can get to the same equation. Okay, so again, because it is single degree of freedom system and one link, you can think of that. Otherwise it is very difficult if it is more than one link. Okay, sometimes more than 2 link, you can treat as much as 2 link maybe. Okay, so in the next class we'll treat 2 link system using similar approach, that is Lagrange-Euler approach. Okay, so that's all for today. In the next lecture we'll be doing dynamic equation of motion of a 2 link manipulator using Lagrange-Euler approach. will also study the parts of general dynamic equation of motion. So what does each of them signify? So that is what we'll be doing in the next class. For today, that's all. Thanks a lot.